Hello, so in this video we are going to start talking about this idea of exponentials. Then later on we'll move on to talking about logarithms as well. Now, if I say exponentials to you, usually I follow it up with another word as well. So I usually either say exponential growth, okay, or I sometimes say exponential decay. And actually that's the perspective that I want you to look at exponentials from today. Now in this video I'm only going to look at it from the perspective of exponential growth, on the basis that if you understand everything you need to with exponential growth, you'll also understand everything you need to with exponential decay as well, because of course decay is just growth but in the other direction, okay? So it's the same principles, it's just happening in the other direction. Okay. Now, exponentials are really important in everyday life. They're probably the most natural type of growth and the most commonly found type of growth. Okay. Instances such as populations or interest rates or radioactivity all follow this idea of exponential growth. They're also one of the fastest types of growth. So what I'm going to do to illustrate this, I'm going to actually look at money, okay? Because of course money appeals to all of us, I'm sure. So just for the sake of this video, I'm going to look at how money is going to grow through time. And I'm going to look at different types of growth in order to give you something to compare exponential growth against. Then hopefully you'll better understand what exponential growth is and why it's different to other types of growth. Okay, so first of all, a bit of notation. Well, first of all, I'm going to look at growth which is happening through time. Okay, so just for the sake of convenience, I'm going to let the letter T represent things happening through time. Okay, and let's suppose in this case, I'm going to look at time in the case of years. Okay, so basically each unit of time is going to represent a year. So if I let t equal 2, that's going to represent 2 years. If I let t equal 10, that's going to represent 10 years. So I'm looking at a time scale with the units of years. Okay, and I'm also going to look at the amount of money which I have. Okay, so that's my other variable that I'm going to look at. Okay, and the money is going to be in terms of pounds, okay, but really it would work in any currency you like. And just for the sake of convenience, I'm going to let the letter Y represent the amount of money I have. Okay, so two variables going on here. I've got time, which is working in the units of years, and I'm going to let T represent the letter represent time. Okay. And then I've also got the amount of money which I have, and that's going to be in the units of pounds, and I'm going to let Y represent the amount of money I have at any particular time. Now, what's really important here is that if I put money into a bank account, nearly always they will offer you interest, okay? So in other words, if I have an amount of money and I go and put it in a bank account, nearly always the bank account will offer me interest. That's kind of a little thank you from the bank to kind of say thank you for letting me for trusting us with your money. Because of course the bank will then use your money to make investments and earn money for themselves. So they give you a little bit of that money back in terms of interest, okay? So really what I'm focusing on here is how money is growing in a bank account, and the reason why my money is growing is because of this little thing called interest, okay? Now, what I'm going to do is I'm going to look at the amount of money I have in my bank account at the start, okay? So I have an amount of money in my bank account at the start, so this is all my money here. Okay, suppose it's all in coins, all my money, okay? And I've got all my money here at the start. Okay, and then I'm going to apply interest. I'm going to leave it in my bank account for some time, going to accrue interest, and then I'm going to see, well, how much money do I have at the end of some period of time? So basically, I'm going to look at how much money I have in my bank account after every single year. Okay, so hopefully that makes sense. So first of all, I'm going to come up with an equation for my money. So just remembering Y is the amount of money and T is the amount of time. I'm just going to write different equations to see how my money grows, okay? So the first equation I'm going to look at is Y equals 2T, okay? Y equals 2T. Now what this basically means is that the amount of money I have in my bank account at any particular year will just be 2 times however long I've left it in there for. So let's actually create a little table here to see what's going on. So I'll just put a little table in down here. Okay, and basically I'm just going to see how much money I have at the end of each year. Okay, so at year 0, fairly obviously, that's at the start of my bank. That's the start of my bank account when I first put money in. Let's suppose I don't put any money into my bank account. Okay, so if year 0, I don't put any money in my bank account, so I just leave it in there, and I just trust that the bank account is going to give me interest. Now in reality, it's not going to work like this, but let's just for the sake of simplicity. Okay, all I'm simply doing here is I'm just simply sticking 0 for T into this equation. Okay, so T equals 0 in that equation, and I get 0 out the other either side. Okay, great. So how much money will I have then after 1 year? Well, if I stick t equals 1 into that equation, 2 times 1, that should be 2. So in other words, after 1 year, I should have £2 in my bank account. Hooray, great. Okay, let's see what happens after 2 years. So if I stick t equals 2 into this equation, well, I get 2 times 2, which is 4. So that means the amount of money which I have will be £4 after 2 years. Okay, so it's slowly growing. Let's keep going then. So if t equals 3, the amount of money I should have in my bank account should be £6, because 2 times 3 is 6. And then for 4 years, I should have £8. And then after 5 years, I should have £10. So all I'm literally doing here is I'm just sticking however long I've left it in my bank account, okay, so whatever my t is, and I'm sticking in this equation here to find the amount of money, okay? Now, if I'm going to sketch this, I should get a graph that looks something a bit like this, okay? So if I'm going to sketch this, I should get a graph that looks something like this. So along my x-axis, that's going to be the amount of time that I've left my money in my bank account. So that's my t. And then along here, that's the amount of money that I have in my bank account. So my x-axis, the amount of time I've left the money in the bank account for, and then along my y-axis, the amount of money I actually have. Well, okay, if I sketch this graph, okay, so if I sketch t against y, then basically I get a graph that looks like this. So I get 0, 0, then 1, 2, and then 2, 4, and then 3, 6, and so on. So in other words, I get a graph that looks something like this, okay? So it's a straight line graph, and all that means is that every single year I get another £2, okay? So the type of growth that I would give for this particular situation would be something called linear growth, okay? The reason why it's linear is because it's growing by the same amount every single year. So you can see every single year I'm getting an extra £2, okay? So every single year I'm getting an extra £2. So in other words, it's increasing by the same amount every single year. And the amount that it's increasing by is £2. Now, of course, it just so happens that in the original equation, I could have seen straight away that it's growing by £2 every single year, because that's what that thing there literally means. That's what the 2 there literally means. It corresponds to the gradient, which means that every single time I go across by 1 year, it goes up by £2. Every single time I go across by 1 year, it goes up by £2. Okay, that's what that number there literally says. Okay, so if I change that then to be something else, for example, y equals 5t, you can see that because that number there has changed to 5, it means that every single year I'm going to get another £5 in my bank account. Okay. Now I could also change this if I don't put £0 in my bank account at the start. Let's suppose I put £10 in my bank account at the start. All I'd have to do is add 10 on the end here, okay? And then that would change the amount which I put in the bank account at the end. So in other words, there is a kind of thing which is adding on the end there, okay? It's kind of a plus C, where that plus C is the original amount of money that I put in my bank account. So in this case, I've got plus 0, which means that I don't put any money in my bank account at the start, but it still grows by £2 every single year. So that's linear growth. Basically means it's growing by the same amount every single year. Okay, so that makes sense? Okay, so now let's consider a different situation. Let's suppose now that the amount of money that I have in my bank account every single year can be modelled by the equation y equals t squared. In other words, the amount of money I have, which is y, is given by whatever year I'm up to squared. Okay, so let's see how that works, okay? Well, if I start off with year 0, that means that t equals 0. So if I stick that in my equation, I get y equals 0 squared. Well, that's just 0. So in other words, at year 0, I end up with £0 in my bank account. Okay, let's keep going then. So after 1 year, how much money will I have in my bank account? Well, if I stick t equals 1 in this equation, I get 1 squared, which is £1. Now, if I compare that just so far, first kind of year 0 to year 1, if I compare that with the situation I had up here, which was the linear growth situation, you can see that actually the linear growth situation is a better bet for the first year or so. So if I'm only going to leave my money in my bank account for the first year, if I have y equals 2t, okay, you can see that actually I'm better off having a linear type of growth, because I only have £1 if I use t squared, whereas I have £2 after 1 year if I use y equals 2t. Okay, but let's keep going to see whether the linear growth is still better. Okay, so let's see then. After 2 years, well, t equals 2. If I stick that in my equation, I get 2 squared, which is £4. Okay, so at the moment, it's kind of breaking even with the situation I had up here with my linear growth. Okay, because after year 2, I've still got £4. But now let's see how it grows, okay? So at year three, I stick t equals 3 in my equation, and I have £9. Okay, so this is much better than the growth situation I had for the linear growth situation, right? Because after year 3 for the linear growth, I had £6, whereas after year 3 for the t squared growth, I have £9. This is looking good, okay? After year 4, well, if I stick 4 in that equation, I'll end up with £16. Then after year 5, I end up with £25. So actually, even though it's slow to get started, so the linear growth at the start is better, okay, by the time it gets after sort of year 3, I'm actually growing at a much, much faster rate by using t squared, okay? So let's actually have a look and see what this looks like on my graph, okay? So again, all I'm literally going to do is just plot together my t against my y. So my time is on my x-axis and the amount of money I have in my bank account is on my y-axis. So let's see how that grows. Well, hopefully you see that it's just going to be a graph that looks like that, okay? So it's going to start at 0, it's going to start off fairly slow, but then it's going to really start growing really quickly. So actually the type of growth that we can call this can be either, there's a few names which we can call to it. We can call it parabolic growth because of course it follows a parabola, okay, you can see that from the graph. You can call it quadratic growth, which is what it is in this case because I've got t raised to some power, so my amount of time is raised to some power. But actually more generally, just so I can sort of change the power up here, so I can change the power to 3 or 4 or 5 or whatever power I like, I'm going to call this polynomial growth, okay? So this type of growth is called polynomial growth. And the idea of polynomial growth is if you take the amount of time that the money has been in your bank account for and raise it to some different power, okay? So it could be 2, could be 3, could be 4, could be 5, but effectively you're taking the amount of time that the money has been in the bank account for and raising it to some power. That's polynomial growth. Okay, so another type of polynomial growth might be something like y equals t to the power of 10, or y equals t to the power of 30, or y equals t to the power of 50, okay? And the idea is that polynomial growth is in general much quicker than linear growth, which we had up here, okay? So this was polynomial growth with time being raised to some power. Linear growth is if we multiply time by some particular number, okay? So as you can see, for polynomial growth, it's much quicker than linear growth. It might not start out like that, but it does eventually end up being quicker. Now, of course, if I add on some particular value on the end of my polynomial growth, that will just correspond to the amount of money I have in my bank account at the very start. So if I put y equals t squared plus 10, that would simply mean that I start off with £10 in my bank account, but then it would still grow in the same fashion, okay? You notice as well that what it's growing by each time is no longer constant. So for linear growth, when we look up here, you saw that the amount which it's growing by each time was constant. That's the definition of linear growth. Whereas polynomial growth, it's not changing by the same amount each time. So you can see for the amount which it's changing by, but from year 0 to year 1, it's changing by £1. Okay, so it's not a massive amount. But then by the time we get from year 1 to year 2, we're changing by £3. And then from year 2 to year 3, we're changing by £5. And from year 3 to year 4, we're changing by £7. And then by the time we get from changing from year 4 to year 5, we're changing by £9, okay? And you notice that the fact that it's going up by the odd numbers each time is just a characteristic of the t squared, okay? But this is always going to be true. It's not going to change up by some kind of sequence going on in the background. That's polynomial growth. It's not going to go up by the same amount each time. Okay, fine. Now, we've seen that polynomial growth is faster than linear growth. So polynomial growth here is faster than linear growth here. But I think we can come up with an even faster type of growth. So look at the way which I'm constructing my equation. For linear growth, the 2 was being multiplied by the t, okay? With polynomial growth, you can see that the 2 is the power of the t, okay? So what if I end up swapping these two things around? So in other words, I take the 2 and the power is the time, okay? Let's see what happens then. So in other words, if I take y equals, then I take the 2 and then I raise it to the power of t. So in other words, I just swap the order of the t and the 2 around from the polynomial growth. Let's see what happens here, okay? So again, I'm going to bring up my table, okay, and I'm going to see what happens, see what this looks like. Okay, So again, I've got t on this axis, the amount of money in this axis, and let's put 0 in the middle, okay? So let's see what happens after every single year, okay? So first of all, what I'm going to have to do is stick t equals 0 into my equation. Well, if you have a look, we've already done indices together. If I think, what is 2 to the power of 0? Because of course time is now the power. So if my power is 0, because that's the year which I'm looking at, then what is 2 to the power of 0? Well, I know that anything to the power of 0 is 1. Okay, so in this case, I'm going to get £1. Okay, I'm going to get £1 there. All right. Now let's see after the next year. Okay, so after year 1, so in other words, I initially invest £1 in my bank account. Let's see what happens after the first year. Okay, so year 1, t equals 1, stick it in the equation. Well, 2 to the power of 1, that's just equal to 2. Okay, so far, we're better than the polynomial growth, okay? But actually, we're kind of drawing even with the linear growth, because you notice that actually after year 1, we've got exactly the same amount of money as the linear growth, okay? All right, let's see what happens after year 2 then. So what is 2 to the power of 2? Well, that's £4, okay? So at the moment, we're beating the linear growth, because after, of course, year 2 for the linear growth, we only had £4, okay? After the polynomial growth, we had £4. And at this kind of type of growth, we've still got £4. So at the moment, for this particular equation, we're drawing even, all right? But we started off being quicker than the polynomial growth and drawing level with the linear type of growth. All right, so now let's see what happens at year 3. Well, if I take t equals 3, stick it in this equation, what do I get? Well, okay, if I stick 2 to the power of 3, that should be 8. Woohoo, okay. So let's have a look. Well, we're definitely beating the linear type of growth, because of course the linear type of growth at year 3 only had £6. But have a look at the polynomial growth. At year 3, well, they had £9. So at the moment, the polynomial growth is just tipping us. Even though it's slower to get started with, it's just tipping us. But now let's see what happens at year 4. Well, okay, if I take 4, so 2 to the power of 4, that's equal to 16. So at the moment, we're now drawing level again with the polynomial type of growth. Have a look. The polynomial type of growth, we're drawing level. But now let's see what happens with t equals 5. Okay, so with t equals 5, stick that in my equation, 2 to the power of 5, that's equal to 32. Okay, so now we're beating all of the types of growth we looked at so far. It's quicker than linear, it's quicker than polynomial. So with all of these types of growth, okay, it really depends how long you're leaving it in the bank account for. Okay, so if you're only leaving it in a bank account for a short amount of time, it may well be that actually linear type of growth is the quicker type of growth, or polynomial growth might be the quicker type of growth, or even this type of growth may be the quicker type of growth. It all depends on the growth equation that you're using, okay? But I can promise you that if you leave it in the bank account for long enough, or if you're doing it over a longer period of time, I can promise you that this type of growth is always quicker. So this type of growth is always quicker. Now the type of growth, which we call this, you guessed it, is exponential type of growth. So I talked to you a little bit about exponential growth at the start, okay? So exponential growth is always going to be quicker if you leave the money in the bank account for long enough. So after time, exponential growth is always quicker. It'll always be any other type of growth that you can come up with, okay? Now, let's actually draw this. Let's see what this looks like. So if I draw this on my graph, I start here at 1, okay? I start here at 1. And in fact, if I draw the graph, it's going to look something like this, okay? It looks a bit like a parabola, but I can promise you it's not, because if I continue it in the negative direction, it kind of looks a bit like this. So it kind of evens out, and then this axis here is the asymptote. Now, you should recognize this graph, because if you remember in the last video, I talked you through the different types of graph. And I said that an exponential graph has this kind of shape here. So it has this kind of shape here, okay? But let's dig a little bit deeper about what's actually going on with exponential growth. So just a reminder, with linear type of growth, we were increasing by the same amount each time. With polynomial growth, we were increasing it by different amounts each time, but there was some kind of linear sequence that was going on in the background. So you saw it went 1, 3, 5, 7, 9. In other words, that sequence was increasing by 2. So there was kind of an increasing sequence in the background. Okay, so it's increasing by 2 in the background. Right? So that's always going to be true with polynomial type of growth. There's always going to be a linear sequence hiding in the background, okay? But with exponential growth, let's see what happens, okay? So we can basically see that at year 0, we have 2 to the power of 0. And then as we go from year 0 to year 1, what we've effectively done is doubled the amount of money which we've had, okay? So we've gone from £1 to £2. And then from year 1 to year 2, again, we've doubled the amount of money we've had. So we've gone from £2 to £4, okay? And then again, from year 2 to year 3, we've doubled the amount of money. And then from year 3 to year 4, doubled. And then from year 4 to year 5, we've doubled, okay? So this is the characteristic which I really want you to get your head around with exponential growth. It is basically a type of growth which either doubles or multiplies by the same amount every single time. So linear and polynomial type of growth, they were basically adding some particular value. So you saw linear growth, you were adding the same amount each time. Polynomial growth, you were adding, albeit different amounts each time, but there was a linear sequence. So you were still adding an amount each time. Whereas with exponential growth, you're multiplying some amount each time, okay? So as an example, if I give you a different type of growth equation, so for example, y equals, let's say, 5 to the power of t. So you notice this is still exponential growth because the time is the power, okay? But the 5 will just simply tell you what you are multiplying by each time. Have a look here. We saw with this type of situation, with y equals 2 to the power of t, we were doubling each time. And we saw that we were doubling each time because that's what that number down there meant. That was the base, okay? So in other words, the base will tell you what you will be multiplying by each time. So with this equation, you were multiplying by 2. With this equation, you would be multiplying by 5. So you can see it's a much faster type of growth, okay? So the base will tell you what you are multiplying by each time. Now here's my question. It's worth kind of pointing this out. If I go back to y equals 2 to the power of t, but then if I end up multiplying this by some particular value, let's suppose I multiply this by 10, okay? So I do 10 times 2 to the power of t. Let's see how that changes things, okay? So again, I'm going to bring up my table, and I'm just going to evaluate, or I'm just going to investigate what happens here, okay? So if I stick t equals 0 into this equation, well, I get 2 to the power of 0, which is still 1, but then I'm multiplying that by 10. So at year 0, I have £10, okay? Then at year 1, how much money will I have? Well, if I stick t equals 1 in this equation, I get 2 to the power of 1, which is still 2, multiply by 10, that's going to be £20, okay? Then if I stick t equals 2, so after year 2, I'm going to have £40. And then in t equals 3, I'm going to have £80. And then t equals 4, I'm going to have £160. And then after t equals 5, I'm going to have £320. So you notice that because this base down here, the thing which I'm taking and then raising to the power of t, the base, is still 2. And you notice that I'm still doubling my amount every single time. So I'm still doubling my amount every single time. So that still works, okay? This number down here will still tell you what you're going to multiply by each time. But my question now becomes, well, what does this 10 do? How does this 10 change things? So have a look at this compared to what we did up here, okay? Well, for this situation up here, effectively I just had a 1 being multiplied by this, right? I just wrote it as 1 times that, didn't need to write it, okay? So where was that 1 here? Well, look, the 1 was the original amount that I put in. So in other words, let's have a look here, see if it's still consistent. Let's have a look, 10, well, that's still the initial amount that I put in. Okay, so in general, what I can say is that if I have an equation of y equals some number, I'm going to call it a, times by some number g, okay, to the power of t, let's see what's happening here, okay? Well, y is obviously the amount which you get, and t is obviously the amount of time that's been left in the bank account for, okay? But let's have a look down here. What does the g do? Well, the g is the growth factor, okay? It's basically what you're going to multiply by every single time. So it's the growth factor. Or you could call it, if you like, growth factor. You could call it, if you like, the multiplier. That's what you're going to multiply by for every time increment, okay? But then what does the a do? What does the number that you multiply all of that by do? Well, that number corresponds to your initial amount. It's your starting value, okay? So that there is going to be the initial or the starting value, okay? So that is really important. This is the kind of characteristics of exponential growth that I want you to get around, okay? This kind of thing, which I'm just going to put a box around here, is the very thing that I want you to get your head around. It's an equation of this form, but exponential growth is basically a type of growth where you're multiplying by the same amount every single time, okay? And if you have an equation like this, the g, the thing down here, the base, that's what you're going to be multiplying by every single time. Okay, and the a, the thing which you're multiplying all of that by, that is going to be the initial amount you start with. So as an example then, if I give you an equation something like this, y equals 4 times by 3 to the power of t. What that will mean, okay, what that will mean is you're going to multiply by 3 every single time increment. So every time increment, you're going to multiply by 3. And the 4 will tell you what you're going to start with. So you're going to start with £4 in your bank account, and then you're going to multiply that by 3 every single time. So as an example, you're going to start off with £4, okay? Then after 1 year, you're going to have 3 times as much. You're going to have £12. Then after another year, you're going to have 3 times as much as that again. So that's £36. And another year, you're going to have £108, so 3 times as much again, okay? And so on and so on and so on. So basically, you start with £4 and then you multiply it by 3 every single time. That's what the equation tells you. If I give you another example, let's suppose I have y equals 8 times by 6 to the power of t. What that means is that you start off with £8, so I start off with £8 in my bank account, okay? And then I'm going to multiply that by 6 every single time. So let's see if I can do this in my head. Well, 8 times 6, I can do that. That's going to be equal to £48. Multiply that by 6, you're going to get to 40 plus 48, so that's going to be 288, I think. Okay, and so on and so on and so on. It might be slightly wrong, so you might want to check that on your calculator. But the point is you start with £8, then you keep multiplying by 6 every single time. Okay, so hopefully that makes sense. Exponential growth is a type of growth where you multiply by the same amount every single time. That's the important thing there. So in fact, that's so important, I'm going to write it down for you. Okay, so exponential growth is a type of growth. So exponential growth is a type of growth where you multiply by the same amount each time, okay? And it's as simple as that, okay? So if you take nothing else away from this video, learn that definition of exponential growth. It's a type of growth where you multiply by the same amount each time, okay? And it follows this equation here. So y equals a times by g raised to some power, okay? And the t is what's changing each time, and the y is the amount in this case, which you're going to have in the bank account after each year. Make sense? Hopefully it does. Now, because exponential growth is so important, I need to think a little bit more about what the growth is actually doing. I need to understand how you're growing, okay? Because, for instance, if you want to know how quickly the value of an item is growing at a particular instant, to know how much money will be made if that item is sold, okay? So, for example, you're doing investments, you need to know how your money is growing in order to work out the optimum time when you need to make that sale. Okay, or perhaps you want to know the rate of change of a bacterial population. Perhaps it's spreading through the population as it is at the time of this recording this video, and you want to understand how is that growing. Okay, it's essential to know that in order to work out the effective policies that need to be put in place to prevent that growth. Okay, so knowing the growth rate is really, really important. Okay, now the thing is with exponential growth, are you happy that because you're multiplying by the same amount each time? Okay, if I take, for example, the situation of a population, okay? So let's suppose you start off with 2 people in your population, okay? And let's suppose you're going to follow the growth pattern y equals 2 to the power of t. So that's the equation that you're going to use to model this type of growth. In other words, you're going to start off, well, actually, in this case, you need to do 2 times 2 to the power of t, don't you? Because you're going to start off with 2 people in your population, and then you're going to double that each time. Okay, so get that right, okay? So 2 corresponds to the starting value, and this 2 corresponds to the fact you're going to multiply each time. So if you start off with 2 people in your population, after 1 year, let's say the growth time rate is 1 year, okay? You're going to end up with 4 people. And then you're going to end up with 8 people the next year, and then 16 people the next year. And then you're going to end up with 32 people the next. And then you're going to end up with 64 the next after that, and so on and so on and so on. So can you see that because effectively all you're doing is you're taking the amount of people that were in the population at the previous year and then doubling it, the growth rate is proportional to the size of the population. That means that the bigger the population is, the faster it can grow. Does that make sense? Because if you start off with a tiny population, let's suppose you start off with a population of 4. Well, if you double that, you're only going to go to 8, okay? Whereas, if I'm going to start off with a population of 32 people, much bigger, then I'm going to end up with 64 people the next year. So in other words, the size of the population at the previous year will determine the size of the population at the next year, because you're going to double. And that means that the bigger the population, okay, so the bigger population, means a faster growth rate. Okay, so it means that the population can grow faster. So the bigger the population is, the faster it can grow. Okay. Now, I always use the kind of idea of a snowball rolling down a hill. So if I just quickly draw a cross section of a hill here, okay, I know it's not a brilliant hill, but imagine this is just a cross section of a hill. So I've just taken a hill, sliced it in half, okay, and I'm watching a snowball roll down the hill side on. So suppose the snowball at the top of the hill is kind of quite small. But then as the snowball rolls, its surface area will increase because it picks up more snow, which means it's going to grow at a faster rate. So at this point here, the surface area is increasing, which means that there's more surface area for snow to cling to, which means it's going to grow faster. So then by the time it gets here, it's really, really big because it's got a massive surface area, which means it can grow even faster. And then by the time it gets to the bottom, it's an absolutely massive snowball relative to where it started at the beginning because it's got more surface area, which means more snow can cling to it. So the idea is the bigger something gets, the faster it can grow. This is the kind of another fundamental idea, or fundamental characteristic at least, of exponential growth that you need to get your head around, okay? So what this basically means is that the growth rate is proportional to the size, okay? So for exponential growth, the growth rate, in other words, how quickly it can grow, is proportional, okay? So that symbol there means proportional to its size, okay, at any particular time. So the bigger something is, the faster it can grow. That's all proportional means there. So the bigger something is, the bigger the size, the faster it can grow. So the faster the growth rate, okay? And that symbol there just means proportional to. It means it's how it's related, okay? Now, you may have seen this before. If you haven't seen this yet, we will meet it again when we look at differentiation. In this case, I'm letting size represent y. That's the amount of money I have in my bank account, or that's the size of my population, for example, okay? So I know that that must be proportional to the growth rate. So in other words, how is the size of my population changing? So the way which I'm going to write that is dy. That's change in population, okay? D just means change, y is population, or y is size. Okay, so dy means change in population or change in size, and I'm doing that in relation to time. Okay, so by the change in time that I'm looking at. Okay, so in other words, dy is the change in my population size and dt is my change in time. If I compare those two things together, I'm going to get myself a growth rate, because of course growth rate is how your population is changing through time. Okay, so how your population is changing through your change in time. That's literally what that means there. So that's growth rate. And it's proportional to whatever size I'm at the moment, okay? Now, if I consider that my population, my size, if you like, is given by the equation y equals n raised to some power, okay? So n is just constant, and obviously y and t are changing, okay? Then I can basically form an equation from this. So I can say that dy by dt should be equal to k times by y. That's literally what proportional means. That's literally what directly proportional means. It means that my population should just basically be multiplied by some value, and that should be my growth rate, okay? That's what proportional means. It just means multiplied by some value, okay? Could be 3, could be 4, could be 5, it doesn't matter. It's just multiplied by some constant value. That's what the k represents, is the constant of proportionality, okay? So if I formulate this in a little bit more detail then, this means then that when I take dy by dt, that means to differentiate. That means to find the gradient. Okay, so I'll write that in for you. This will become a little bit clearer when we look at differentiation, but it just simply means for the time being, find the gradient. Okay, so imagine we have a graph that looks like this, and I've drawn my exponential graph in a few times now. So that's my exponential graph. That's y equals n raised to some power. Okay, that's my exponential graph. Basically, if I want to find the gradient, what I'm looking at there is at any particular point in time, how quickly is the graph changing? The way that I can determine that is by using tangents. Okay, and it's going to be different depending on which point I look at. Okay, so if I want to find the gradient of this graph, I should just simply take whatever my population size is and multiply it by some particular value. Okay, now when we look at differentiation, we will actually look at calculating what this value is. However, just for the time being, okay, if I take my population equation is something like this, okay, it basically means that I should be able to say that dy by dt, in other words, my growth rate, should be equal to the natural log of 2 multiplied by 2 to the power of t. Now this thing here is my constant. That thing there is my constant, okay? If I take something like y equals 3 to the power of t, then in that case, my growth rate, my gradient, will be given as the natural log of 3 times by 3 to the power of t, okay, times by my population size. But there's one particular base, so 2, 3, 5, 7, there's one particular base where actually the constant out the front is just equal to 1, okay, is just equal to 1. And that particular base, okay, is e. Okay, so that particular base I give e. Now e is actually short for a longer number, so e is actually something like 2.718, and actually like pi, it carries on forever and ever and ever, and it never ever repeats. Okay, so e is a special number. But basically, if I take y equals e to the power of t, so this 2.718, etc., 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 and raise that to the power of t, then it just so happens that in that case, dy by dt is equal to 1 times by its size. So 1 times by e to the power of t. In other words, it's just equal to e to the power of t. So there's no constant there. Okay, so in general, when you're differentiating or when you're finding the gradient or finding the growth rate of your exponential function, there'll always be some number out the front. Okay, so I've just shown you that that's sort of natural log of 2, that's natural log of 3. Okay, but if you consider an exponential growth with a base of e, so 2.718, this really weird long number, then it just so happens that when you find the growth rate of that, it's exactly equal to whatever its size is. Okay, so if I know what the size of a population is, if we're following this equation, y equals e to the power of t, okay, so it's exponential growth where the multiplier each time is like 2.718, it's e, okay, it basically says that the growth rate should be the size of the population, exactly equal to the size of the population. And actually this is so important that we call this the natural base, because it just so happens, this is kind of one of the weird phenomenons in life, that it just so happens that every single type of situation which is growing exponentially has this base as the multiplier. So populations, bacteria, radioactivity, they all have this base as the multiplier for every single time period, which I think is just kind of mind-boggling. It's amazing, okay? Now, it actually just so happens there is a type of, you need to be careful to distinguish between discrete and continuous growth here, okay? So discrete and continuous growth, and I'm going to play on this idea in a little bit. Okay, so discrete growth basically means that the growth is happening at discrete time intervals. It's happening at set time intervals. So with our example of our money, if I scroll right to the very top, our money up here, okay, basically said that our money was changing every single year. So in other words, it stayed, so if I take this situation, it stayed at £10 for the entirety of year 0, and then as soon as the clock ticked over to year 1, then it changed to £20. Then it stayed at £20 for the entirety of year 1, then as soon as the clock ticked over to year 2, it changed to £40, okay? And then it stayed at £40 for the whole of year 2, and then as soon as the clock ticked over to year 3, it stays at £80. So this is what I mean by discrete. It's happening at set time intervals, okay? Now, because most situations in life follow exponential growth in the sense that they're multiplied by some value each time, but because most situations in life aren't discrete, okay, they don't happen at set time intervals, they're growing all the time, we talk about that as continuous growth. So actually, the reason why everything follows a natural base is because things are growing all the time. And because things are growing all the time, it actually follows a base with this magic number here, this magic number called e. Now, the reason why it's called e is because it's the exponential number. It's e, okay? Exponential, e exponential, okay? And it was actually discovered by a guy called Leonhard Euler, okay? So it's sometimes called Euler's. So let me spell that right, E-U-L-E-R, okay, so it's come up with a guy called Leonhard Euler. He was looking at this, and I'll show you exactly the same process, the thought process that he used to derive this particular number now. And the way which we can do this is by actually coming back to our idea of money growing. So let's suppose that we have our money in our bank account, and I'm just going to write it as e to the power of t. Now, hopefully you should look at this equation now and realise, okay, y equals e to the power of t. That means that I'm multiplying all of this by 1, okay, which means that I initially start off with £1 in my bank account at the start. So again, if I draw myself a little table out, if I draw myself a little table out, then what that means is that I should end up with, I should end up with £1 in my bank account at the start, okay? So now let's see what happens. Now, just to make sure I get this right, I'm actually not going to consider it as an exponential situation anymore. What I'm going to do instead is consider it as an interest rate situation, okay? So let's consider it as an interest rate situation. Now, interest rate is usually given in terms of a year, okay? So how much interest will you receive over the course of a year, okay? So let's just suppose the bank is being really super generous, and let's suppose they're giving us 100% interest per annum. That means every single year I will get 100% interest. And obviously the starting amount that I start off with is £1, okay? So my question to you is then, if I'm getting 100% interest every single year, that means whatever I put in my bank account at the start, I'm going to get 100% of it back at the end of the next year. How much money will I have after a year? Okay, so after 1 year is up, how much money will I have? Well, I have 100% of whatever I put in at the beginning. So 100% of 1 is another 1, so therefore I'll end up with £2 in my bank account there, okay? Now, you remember that in the last kind of little thing, I said that E is really useful for if we're considering continuous growth. In other words, growth that is happening continuously. So at the moment, what I'm looking at is discrete growth. I'm basically seeing, well, okay, look at the beginning of the year, then suppose it stays at £1 for the whole year, and then after the first year, so at year 1, the clock ticks over and I suddenly get £2 being deposited in my bank account, okay? But that's not actually how it works in real life. Usually it happens over a much more continuous time period. So let's do the same thing again, but let's suppose, for example, I get that 100% interest rate applied biannually. Okay, so what that basically means is I get it applied twice during the year. So I still get 100% over the course of the full year, but instead of getting 100% at the very end of the year, I get 50% after the first 6 months, then the other 50% after the next 6 months. Let me show you what I mean. So this situation up here was basically looking if my interest rate of 100% was being applied every single year, okay? So every year, okay? So it's 1 year and it basically waits 1 year, then the interest rate is deposited then. Now let's look at the situation if it's applied every 6 months, okay? So instead of waiting an entire year for me to get interest, I'm still gonna get 100%, but I'm gonna get 50% after the first 6 months, and then another 50% after the next 6 months. So 50% here, then another 50% here. So I'm still getting my 100% because it still adds to 100%, but it's happening every 6 months. So it's kind of split over 6 months intervals. Let's see what happens now, okay? Well, I still start off with £1 in my bank account, okay? And then after 6 months, I get 50% of whatever I had at the beginning. So, okay, 50% of £1, that's 50 pence, okay? So in other words, after 6 months, I'll have £1.50 sitting in my bank account. And then after the year is up, I get my next 50% of whatever I had previously in my bank account. So I had £1.50 in my bank account, I get another 50% at the end of the year. So 50% on top of £1.50, it's gonna be 75 pence on top. So that's gonna be £2.25. So you can basically see that after the year is up, it's actually a better situation if the interest is given to me every 6 months rather than after 1 year, okay? Because I have another 25 pence in my bank account. You know, that's probably enough to buy like a chocolate bar or something, I don't know. But now let's see what happens then if we keep increasing the time intervals at which you can accrue interest, okay? So let's suppose that instead of doing it every 6 months, let's suppose instead that it's accrued every 3 months instead. So it's accrued 4 times over the course of the year. Okay, so this is now going to happen every 3 months, okay? So basically what that means, I take the 100% interest that I need to accrue over the full year, and I basically split it into 4 equal parts. So in other words, I get 25% interest after the first 3 months, another 25% interest after the next 3 months, so that's 6 months in total since once I put the money in the bank account, then another 25% after 3/4 of a year, so after 9 months in total, and then after the full year is up, that's when I get my final 25%. So let's see what happens here. So I need to basically keep on accruing 25% on top of whatever I previously had in my bank account. So after the first 3 months, I'm going to end up with another 25%, so that's going to be £1.25. And then I'm going to end up with another 25% on top of the £1.25 that I had in my bank account at the end of those first 3 months. So another 25% on top of that, that's going to be £1.56, okay? And after the next 3 months is up, that's going to be £1.95. And then finally, after the full year, I get another 25% on top of this £1.95, and that's going to give me £2.44. Okay, so this is going to be interest which is accrued every 3 months, so 4 times during the year. Okay, so you can see that suddenly I end up with a better rate than if I just got the interest after the first year or after every 6 months. Okay, I get a better interest rate, right? But I think we can keep on going. What if I want to get interest, so this 100% interest, what if I wanted to get it every single month? So in other words, 12 times during the year. Let's see how that changes things. So okay, if I'm accruing interest every single month, then basically what I'm going to have to do each month is add on an interest rate of that 100% divided amongst my 12 months, okay? So whatever 100 divided by 12 is, that's how much money I'm going to add on every single month, okay? So every single month, I'm going to get another 100 divided by 12% amount of interest, all right? So let's actually work this out. So we got £1 there, okay? After the first month, I'm going to end up with £1.08 in my bank account. And actually, I'm just going to fill in this table just to see how much money I get after the first year, to see how it changes. Okay, so you can basically see that after a year, so basically if I accrue interest, so this 100 over 12% interest every single month, then it means that after the first year, I end up with £2.61 in my bank account, okay? Now, I am going to keep going with this. So I've done every sort of year, I've done every 6 months, I've done every 3 months, I've just done every single month. But now the next place that I want to go is every single day. Okay, or maybe every single week or something. So rather than doing it this way by thinking, well, okay, what am I going to have to add on as interest every single time? What I'm going to do instead is come up with a formula that will streamline this process. Okay, so obviously I start off with £1 in my bank account. And then what I'm doing by this is I'm literally multiplying by an amount every single time. The amount which I'm multiplying by every single time is going to be 100, because that's the 100% interest, divided by, in fact, I'm not going to multiply that, am I? Because I need to multiply by 100 plus whatever interest I'm adding on. So 100% plus whatever interest I need to amount to every single month. So as an example, when I was looking at every single month, I was taking this 100% interest that I'd be adding on in total over the course of the year, and then dividing it by the number of times I'm actually adding on this interest. So in this case, I'm adding it on 12 times because it's every single month. So in other words, what I'm doing is I'm taking this 100% interest and I'm dividing it by the number of times that I'm actually adding on, or I'm actually calculating my interest. Then how many times am I going to multiply this? Well, I'm going to keep doing it over and over again. So I'm going to do the 100% plus 100% over n, that's the interest that I'm adding on. And I'm going to keep doing that as many times as I need to calculate it. So in other words, I'm going to take this value, this thing in the brackets, and I'm just going to raise it to the power of n. That corresponds to the number of times that I'm actually physically calculating my interest, okay? Now, instead of writing 100% every single time, I'm just going to write it as 1, because that's the same, okay? Instead of writing 1 times that, I'm going to get rid of that. And again, that 100% there, I can just write that as 1. Okay, so this is a really, really fundamental idea. The amount of money that I should have in my bank account after a year should be given by this, where n is the amount of times that I'm calculating that interest. And of course, the amount of the time intervals are always constant. Okay, now if I do that, I can basically see how much money I will have at the end of each of my bank accounts, or at the end of each of my years. Okay, so I've just seen, for example, that if I calculate my interest every single year, I will end up with £2 at the end of the year. So let's put up here the amount at the end of the year. So end of the year. Okay, and let's suppose this is going to be the frequency at which I'm calculating my interest rate. So for yearly, I get £2 at the end of the year. Okay, I've just seen as well that for every 6 months, okay, I end up with £2.25 at the end of the year. We did that together. Okay, I also saw that for every 3 months, I end up with £2.44 in my bank account at the end of the year. Okay, we did that one together. I've just done every month together, so monthly. Okay, so when I did monthly together, we saw that we ended up with £2.61 in our bank account. Okay, if I wanted to do every weekly, so I want to do every single week, okay, all I would simply do is put n equals 52 in this formula up here, because of course the n corresponds to the amount of times that I'm calculating that interest. So if I put 52 in there, I would end up with, at the end of my year, I would end up with £2.69. Okay, if I wanted to do every single day, okay, so if I wanted to do daily, then fairly obviously I would put 365 as n into my formula, okay? And if I did that, I would end up with £2.71. Now, just because I know money can only have two decimal places here, but just for the sake of illustration, I'm going to actually keep the decimal places running. So I'm going to allow more than two decimal places, just to show you what I get. So if I do every single hour, okay, so if I do it hourly, calculate the interest every single hour, work out the number of hours there are in a year, then I end up with, at the end of the year, I end up with £2.71.8, okay, so 2.718, okay. If I wanted to do this every single second, okay, so every single second, the way which I would do this is calculate the number of seconds there are in a year, stick n is that number in there, and I would end up with 2.71828. Okay, so in other words, the more frequently that I calculate my interest, I'm getting continuous exponential growth. Are you happy? Because instead of calculating it every single year, which is what we're doing with our first examples, suddenly I'm doing it every single second. And in fact, I can do it even quicker than this. I can do it every single nanosecond or microsecond or picosecond if I wanted to, okay? And it's just working out the number of picoseconds in a year and sticking n into this formula. So in other words, what I can say is that as I make n bigger and bigger and bigger, in other words, as I calculate this more and more and more, so over smaller and smaller time intervals, I'm going to write it like that. That means the limit as n gets bigger and bigger and bigger, because of course n is the amount of times that I'm calculating my interest, and of course if I'm calculating it more often, n gets bigger, okay, because I'm doing it more often, so I'm doing it more times, okay? And I take this original formula I was using, so 1 plus 1 over n to the power of n. So in other words, as n gets bigger and bigger and bigger, this thing, the limit, so this thing approaches some particular number, okay? And the number is, I'm going to write down as several decimal places, and I might need to scooch this over a little bit. So the number is 2.718, 2818, 28459, 045, 235, 245, 235, 60287, 47135. I think that's right. And it carries on forever and ever and ever. So as I keep calculating this over shorter and shorter time intervals, so I'm doing it more often, this thing approaches this number and it carries on forever and ever and ever like this. And in fact, we give this a special name. You guessed it, we call it E. So if you're ever wondering what is E, where does it come from, it's basically what happens if you have an exponential growth situation. In other words, a situation where your population, bacteria, radioactivity, whatever it is, okay, your size is basically multiplying by some amount every single time. If that's multiplying over a continuous growth, okay, so it's not happening at set intervals, it's not happening like every single year or every month or something like that, but what happens if it happens every single time? So it happens all the time, it's never slowing, it's never stopping, okay? If that happens, you basically get E, okay? And that's where E comes from. So E is a really important base, it's the kind of the natural base. So I said that I would also talk about logarithms, like what logarithms are and why they're important, okay? So let's go back to our growth situation. We've just looked at exponential growth. We've seen why E is important. That's really, really good, okay? But now I want to really get under the skin of logarithms. Well, the good news is a logarithm is pretty much exactly the same as an exponential, but it's just looking at it from a slightly different perspective. Let me show you why. Okay, so let's suppose I have a growth situation like this. Now, are you happy? It is exponential, okay? Because obviously every single time I'm multiplying by the same amount every single time. In this case, I'm multiplying by 2. So if I wanted to give an equation which would describe this, I could say, well, okay, in order to get from time to the amount, okay, I could just simply find y by taking 2 and raising it to the power of time. Okay, that would give me, that's basically saying, you give me time and I will tell you how big something is, okay? So y equals 2 to the power of t literally says, you give me time, I'll tell you how big it is, all right? What if I wanted to go back the other way? What if I wanted to ask you the different question? What if I wanted to ask you, this is how big something is, how long has it been growing for? Okay, so this equation, y equals 2 to the power of t, this simply says, you tell me how long something's been growing for, and I'll tell you how big it is, okay? What if now I wanted to ask the question, well, I'll tell you how big it is, you tell me how long it's been growing for. In other words, you want to go back the other way. Well, fortunately, you can really easily do that, okay? And it's using the idea of a logarithm. So in this case, the amount of time that something has been growing for is given by this thing called a logarithm, which we write as log for short. We need to know the base. We need to know what the growth factor is. We need to know what we're multiplying by every single time. So in this case, we know it's 2. That's given to us, okay? So the base kind of goes down here. It's a little 2 just down below the g, okay? And then the thing which goes in here is effectively the size. So it's the y, okay? So all this says, okay, this thing here just says, you give me time, okay? You give me time, and I will tell you the size, okay? Whereas this equation down here is different because it says now, you give me the size. You give me size and I will tell you time. So those are the two types of equations you need to get your head around, okay? An exponential equation says, you give me time and I will tell you size. A logarithmic equation, the thing which I've written down there, says, you give me size and I'll tell you how long it's been growing for, okay? Now, we've just seen that there's a really important exponential equation, y equals e to the power of x, okay? There is also a logarithmic equation for this, okay? So if I wanted to convert this to a logarithm, I could write this as, well, I'm not going to worry about the y's and the x's, so don't get confused with the y's and the x's. I could write this as y is equal to log to the base e of x, because in this case the base is e, okay? Don't get confused with the y's and the x's, I'm just simply writing this as a function of x, okay? So the y's and the x's, don't get particular with them. They're just simply numbers, they're just simply values, okay? So even though this isn't quite true, okay? So therefore, I could give this a special name. If I have y equals log to the base e of x, okay, y equals log to the base e of x, because e is talking about growth in the natural world. It's natural growth. It's the thing which describes natural growth in the real world. Then the logarithm should be describing natural stuff as well. Hence, it's sometimes called the natural logarithm. Okay, so the natural log or the natural logarithm. And the way which I abbreviate that is to ln. Okay, the reason being is because the guy who came up with it was French, okay, and they say logarithm naturel or something like that. Sorry for my bad accent, okay. But the idea is that it's logarithm naturel or the natural log, okay, and in this case, it's going to be natural log of x, okay. So that's the idea of a logarithm. It's a way of converting exponentials into a way, so instead of saying you give me time and I give you size, it's a way of saying, well, actually, you give me size and I give you time. Okay, so it's the other way around, right? So as an example, just a quick way of converting between them, if I give you an equation like this, y equals 3 to the power of t, okay, if I wanted to convert that, okay, in fact, I could probably convert that nice and easily, actually. If I just give you 3 to the power of 2, okay, equals, of course, 9, okay, then what I can do is convert this into a logarithmic equation by saying that 2, that's the thing I'm interested in the time, okay, that's equal to log to the base is 3, of whatever size I'm at, okay, so those two things are exactly equivalent to each other, it's just they've been rewritten in slightly different ways. So in general, if I have a number n, and I have a base, which is b, and I raise it some power p, okay, so if I use this notation, then I can write this as a logarithm by saying p is equal to log to the base b, so the b goes down here, of whatever my size is, so in this case is n. So this is how you convert between logarithms and exponentials like that, okay? Now, if I write something like this down, I can actually work out what the value is, okay? I can actually work out what the value of something like this is. So this says log to the base 9 of 81. That's how you verbalize it. Log to the base 9 of 81. So really, the way which I want you to think about this, in order to work out what the answer to this would be, okay, is to simply say, well, I know my base is 9, and I know my answer is 81, and I'm interested in my power. So all I want you to think is, what power do I raise 9 to in order to get 81? Well, hopefully you realise that the power I raise 9 to get 81 is just 2. Okay, so the answer to this would be 2. Okay. Another example, if I give you log to the base 3 of 243, okay, you're literally saying, well, okay, 3 to the power of what is going to give me 243? Well, hopefully you realise that should just be 5, because 3 to the power of 5 gives me 243. What if I gave you something like this? What if I gave you log to the base 2 of 256? That literally means, what power do I raise 2 to in order to get 256? Well, that power has got to be 8. Okay, so that power's got to be 8. Now, the thing is, what if you're not sure? Because it's not always going to be a whole number, right? It's not always going to be a whole number. Is there a way of doing this on your calculator in case you weren't sure? Well, yes, there is. Let me bring my calculator up and show you. So, okay, let's just pick some numbers at random. Let's suppose I want to do log to the base 5 of 100, like so. Okay, and I wanted to work out what this is. Now, if I try and think about this logically, I'm basically saying, okay, well, I've got 5. What power do I have to raise 5 to in order to get 100? Well, I'm not sure you do raise it to an integer power, but there is still a power, it's just I can't work it out. So this is where the calculator is really useful, okay? So it'd be slightly different on different calculators, but you should have in the top right-hand corner this button here, which is a logarithm button, okay? This logarithm button, if I click it, will bring up 2 empty squares. You see that there's a square down here for the base. So in this case, my base is 5, okay? Then to move inside the brackets, I'm just going to move to the right by clicking that key there. You can see my cursor is now inside the brackets, and I now put my 100, okay? And now if I click enter, it will return me the answer, okay? So this is going to be 2.86, okay? So it's fine to 2 decimal places. If I give you, for example, something like this, ln, so the natural log of 3, okay? This is basically saying, well, in this case, the base is e. So e to the power of what gives me 3? Well, I don't know. So all I need to do is just type down here. I can either type log and then find the e on my calculator, which is just down here. So it's just in the yellow. But actually, there is a dedicated button for the natural log. You see it's just below the logarithm button. It's the ln here. So if I hit that, and if I now type 3, close my bracket, hit equals, it will return me my 1.10 to 2 decimal places. So 1.10 to 2 decimal places, okay? So just be aware, there are buttons on your calculators which will help you work with logarithms automatically. So we've looked at quite a lot today, okay? Just to recap what we've done. We've looked at, first of all, the idea of growth, okay? So we first of all looked at the idea of growth, and we've looked at the different types of growth. And you should now be able to tell me why exponential growth is so different to linear growth, to different to polynomial growth. It's the fastest type of growth that you can get. And it's basically what happens if you multiply by some amount each time, okay? So in general, if I have some value, which I start off with, so that's a, that's my initial value, okay, so that's my initial value, so I'm going to call it I0 for initial value, okay? Then I'm going to multiply that by some growth factor, so this is going to be growth factor. This is my multiplier each time. And the really important thing is that the thing which is changing is the power of the multiplier. So I can call it t, I can call it x, whatever. That just simply corresponds to how many times I'm going to multiply by. Okay, so how many times I'm going to multiply my initial value by. Okay, and we've seen that there's a really important number in exponential growth. It's e, it's 2.718, etc., 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 and it carries on forever and ever and ever. It's basically the number which gets out when you've got a continuous exponential growth situation. So if you've got kind of discrete growth, okay, you'll probably use like 2 or 3 or 10 or 5. So for example, growth is only happening yearly. But if growth is happening all the time, it'll follow this natural growth where the base is like 2.718, etc., etc., etc. Now we've also looked at logarithms, okay? And the idea of a logarithm is it's just simply the reverse of an exponential, okay? So in other words, if I have y, let's not use y actually, let's use n is equal to some base to the power of p. In order to convert this to a logarithm, I would say that p, because I'm interested in the power now, okay, so p would be log to the base b of whatever size I'm at, okay? But don't think about it necessarily as the formula directly. Just think, with an exponential growth situation, so with an exponential, this thing here, it simply says, you tell me how long your thing has been growing for, and I'll tell you the size, okay? Whereas with a logarithm, it's asking it from the different perspective. It's basically saying, you tell me the size, and I'll tell you how long it's been growing for. So it's really just looking at exactly the same thing, but from 2 different perspectives. Now, you should be aware that you will have laws of logarithms, okay, and you will meet those again. You'll also look at how to solve equations and things like that with logarithms. But hopefully what this video does, it gives you more grounding over what exponentials are and what logarithms are.